Now that we've discussed the basics of irreversible acid-base reactions and how to calculate their pHs and pOHs and hydronium ion concentrations and hydroxide ion concentrations, we need to take the next step and look at advanced acid-base calculations, and these will all deal with either weak acids or weak bases and the extent to which they can ionize, which will not be completely. So we're talking about all of the acids that are not on our list of strong acids that exist in nature, and of course the same goes for the bases as well. Rather than taking you through theory, I thought I would just do a quick problem or two illustrating how we use what we've mastered in equilibrium and apply it to an acid-base system. So on PowerPoint slide number 10 in your advanced acid-base notes, and these are already posted on pause, we are confronted with the following problem. Sore throat medications sometimes contain the weak acid phenol. We have a 0.1 molar solution of phenol, and we have a pH of 5.43 at 25 degrees Celsius. And we want to find the Ka for the phenol acid at this given temperature. So I'm going to actually render phenol as HA. And I want to show the dissociation of this weak acid in water. So of course water will be the Bronsted-Lowry base, if you will. And we will produce, albeit reversibly, in a process that's governed by the Ka of phenol, hydronium ion, H3O plus, and the conjugate base of phenol, which I'm going to render as A minus, but more properly it is called phenoxide. And just like we did with equilibrium, we're going to construct an ice diagram. So initially we know that we have a 0.1 molar solution of phenol. There is no hydronium nor conjugate base formed before the reaction begins to dissociate. Some amount, we're going to call that amount X, will dissociate, and so consistent with the stoichiometry of the reaction, we will gain X molar of hydronium and A minus, and we will lose X molar of HA. So at equilibrium we have 0.1 minus X, and then we have X molar of hydronium and X molar of A minus. Now typically with all of these pH calculations we can ignore the extent of ionization of the acid because usually the initial concentration of the acid is at least 1,000 times greater than the value of Ka. The way I'd like for us to approach this problem is determine what this Ka is going to be, and then we can begin to see if we were justified in applying this approximation. So X, we know how much hydronium we have because we are told that the pH of the solution is 5.43. And last Wednesday we discussed how we can calculate the hydronium ion concentration from the pH. Now, since X is equal to the hydronium concentration, X is going to be equal to 10 to the minus 5.43. The initial concentration of the acid is 10 to the minus 1. So if we're justified in ignoring the contribution that X brings to this equilibrium expression with respect to the equilibrium concentration of HA, then X should be much greater than HA. And if you look at this algebraically, 0.1 minus 0.0000 digit, and I'm not going to input this on my calculator because that's just trivial and we can do that on our own time. We realize that the answer should be approximately equivalent to 0.1. So I think we're justified in making our approximation. So X squared, which is 10 to the minus 5.43, quantity squared, because whenever I make hydronium I also make conjugate base, divided by 10 to the minus 1 is equal to Ka. And as I simplify, I have 10 to the minus 10.86 divided by 10 to the minus 1. And even though this isn't in fully simplified form, I think you'll get to the point that it's 10 to the minus 9.86. This will be on the order of 10 to the minus 10. Now, to put this into perspective, this acid is so weak that if I have 10 billion molecules of phenol, one of them will dissociate. That's a pretty weak acid. So going back to our initial question, we've answered what the ionization constant is. Now, what about the degree of ionization? Well, let's go back. We know our Ka is equal to 10 to the minus 9.86. We know that our concentration of hydronium is equal to 10 to the minus 5.43, and we know that the concentration of our original undissociated acid was 10 to the minus 1 molar. And of course, hydronium ion concentration is also given in terms of molarity. The percent ionization is a pretty simple calculation. Where it is mathematically equal to the concentration of hydronium at equilibrium divided by the concentration of undissociated acid from the beginning. So if you have a strong acid that completely dissociates, its percent ionization is 100%. In this case, we have 10 to the minus 5.43 divided by 10 to the minus 1. That is 10 to the minus 4.43, which is 10 to the minus 2.43%. So this is on the order of 0.00 something percent. Certainly indicative of a weak acid. Now we know it's a weak acid because the pH is significantly greater than 1. If it was HCl and it was a 0.1 molar solution, it would have a pH of 1. This has a pH of 5.43. We know that it is a weak acid by virtue of its Ka being such a negligibly small positive number. And we also have an indication that it's a weak acid by virtue that its percent ionization is so close to 0%. So let's actually go and check the solution for this. Pull up my PowerPoint slide. So notice that they're giving us the setup. We find the hydronium is 3.7 times 10 to the minus 6, which is going to be 0.00037. Very little hydronium. We find that the Ka is 1.4 times 10 to the minus 10, as we predicted. And we also find that the percent ionization is 0.0037%. So it looks like we successfully calculated all the properties that are given in this particular problem. So in recap, we can use the ICE methodology to compute pH, to compute hydronium ion concentration, to compute Ka, to compute percent ionization. These are issues we'll be discussing in class later today, but this gives us a nice start on how to attack some of these advanced acid-base equilibrium problems.